Electromotive force, or EMF, and internal resistance. Here we have a simple circuit, and we're measuring the potential difference across the supply, in this case a cell, measuring the current through the circuit with an ammeter, and we have a variable resistor that I've given the symbol capital R. If we plot a graph of the terminal potential difference in volts against the current in amps as we change the value of the resistor R, starting with an infinite resistance and going to zero resistance, we get a line something like this. So this is the maximum current we can get from the supply when the resistance was 0, and when we have an infinite resistance, this is the maximum terminal potential difference we get, which is called the EMF, or electromotive force, and is given the symbol epsilon. So the EMF is the potential difference that the supply provides when on open circuit, or with infinite resistance, i.e. when zero current flows. So as soon as we allow a current to flow, the potential difference that the supply can provide reduces. This is down to the internal resistance of the supply. It needs to use some of its energy to pass the current through itself. It acts as though there is a small resistor in series with the supply. As I've shown here, a small resistor I've given the symbol lowercase r. So at this point here, with zero load resistance, we can find that the current is equal to the EMF over the internal resistance. We know that for a supply, current is equal to potential difference divided by resistance, or more strictly speaking, it is equal to the electromotive force of the supply divided by the total resistance. This is the resistance in the circuit plus the internal resistance of the supply. We can write this as current is equal to EMF over internal resistance plus load resistance. Rearranging this, we can say that the EMF of the supply is equal to the current multiplied by the external resistance, or load resistance, plus the current multiplied by the internal resistance. Of course, in a series circuit, the current is the same all the way round the circuit. We can also say that the terminal potential difference, V, the potential difference we actually get from the supply, is equal to its EMF minus the current times by the internal resistance. This is the potential difference lost getting the charge across the supply itself. Let's look at a simple problem. A voltmeter with a very high resistance is placed across a battery and gives a reading of 14 volts. When connected across a 22 ohm resistor, a current of 0.6 amps flows. What is the internal resistance of the battery? Well, when we use a very high resistance voltmeter, we can assume that we are reading the EMF of the supply. So using the equation EMF is equal to current multiplied by external resistance plus current multiplied by internal resistance, we can rearrange to get the internal resistance is equal to the EMF minus the current times external resistance divided by the current. The EMF being 14 volts, the external resistance being 22 ohms, and the current 0.6 amps. So we can add the numbers to get this, and when we work it out, we get an internal resistance of 1.3 ohms. Now for the second part of the question, if a piece of copper wire is now placed across the terminals, what current will flow? Well, copper wire has a very low resistance, so we can assume that the battery has been short-circuited. And so, from this term, the resistance is 0, and this simplifies to EMF is equal to current multiplied by internal resistance. We can rearrange that to get the current equal to the EMF divided by the internal resistance, which is 14 volts divided by 1.3 ohms, giving a current of 10.8 amps. Incidentally, this answer actually comes out at 1.3 recurring, and if we'd kept the full answer to this in our calculator to use here, we would have got an answer of 10.5 amps. We can rearrange this to give current is equal to EMF over internal resistance, with an EMF of 14 volts and internal resistance of 1.3 ohms, gives a current of 10.5 amps. Incidentally, if you try the calculation of 14 over 1.3, you'll find it comes out at 10.8 amps. The answer up here is actually 1.3 recurring, and I've kept the whole number in my calculator to use in this calculation. You must do this to avoid rounding errors. When doing multiple calculation problems like this, it's generally better to keep the full numbers in your calculator as you work to avoid rounding errors as you go through. A car starter motor needs a very large current, and so a car battery must have a very low internal resistance to allow this large current to flow. The mains has a very low internal resistance and can produce fatal electric shocks. It's particularly dangerous when you're working outside on damp ground, as the resistance through your body to earth will be reduced, producing a larger current. Extra high tension supplies, or EHT supplies in schools, are capable of producing an EMF of around 5,000 volts, but they have a very high internal resistance built in to prevent them providing a lethal current. Rearranging, we get that the current is equal to the EMF divided by the internal resistance, the EMF we were given of 14 volts, the internal resistance we found previously of 1.3 ohms, giving a current of 10.5 amps. Incidentally, 14 divided by 1.3 actually would give 10.8 amps. But my answer here was 1.3 recurring. I've quoted it to two significant figures, as my data was only quoted to two significant figures, but I've kept the entire number in my calculator to use down here, giving me a more accurate figure for the current. It's very easy, during multiple calculations, to build up quite large rounding errors. So always quote your answers to a small number of significant figures, but keep the number in your calculator.